Well, hey there, YouTube. How you doing out there today? This is Mr. Thompson, and we're going to go ahead and keep talking about the lungs and stuff like that. We talked about how the lungs look, and we talked about how the breathing parts work. Now, let's go ahead and get into the gas exchange part. But hey, before you do that, what I would really like you to do, if you like my content, I want you to mash that subscribe button. Just like jam your thumb so far into that subscribe button that there's like nothing left, okay? Just get an old phone, watch this video on it, break the glass, okay? Just get after it. Hit that little bell icon, just ring it. Get a hammer. I don't have a hammer. This is my channel, so it doesn't matter. And just hit it. Hit the bell. This is the only way you're going to know that you get the new content. I thrive on this stuff. I live on this stuff. The channel lives on this stuff. So just mash and ring or something. I don't know. Tell you what. How about we pretend that never happened and we'll just keep that between you and me, okay? Don't post it anywhere, anything super weird like that. And let's just talk about gas exchange, right? Okay, good. All right, so here we are in the alveoli, also known as the gas exchange, and we're going to talk a little bit about how we bring that oxygen in and we get that oxygen out. All right, so with gas exchange happens in two places, basically. Okay, so the first one is between the blood and the air within the alveoli, and the other one is across the blood-air barrier. Now we're going to have another gas law that comes in here. This exchange is going to be dependent upon the partial pressures of the gases involved and the diffusion of those gases, the diffusion of the molecules between the gas and the liquid. Now, gas diffusion occurs just like regular diffusion in response to concentration gradients, high concentration to low concentration, okay? And so the rate of diffusion is going to depend on particular gas laws. So just like how we drive pulmonary ventilation by changing pressure, how much and how fast you diffuse oxygen, for example, into your tissues is going to be dependent upon the pressures and the amount in that particular medium. So Boyle's law, that one that we looked at, that the pressure and the volume thing, is going to come into play. Okay. Now another one that we're going to be looking at is Dalton's law. This one, it basically says within a mixture of gases, each gas is going to contribute to the total pressure in response to its relative abundance. This is also known as Dalton's law of partial pressures. So air is a mixture of several gases. Now it's primarily three gases, but there's a lot of gases in there, okay? So within this mixture of gases, okay, we have our partial pressures. And so this is the pressure that's exerted by each gas within the mixture. So if we look at the atmospheric pressure, standard atmospheric pressure, it's 760 millimeters of mercury. Based on how abundant the different gases are, each one is going to exert a partial pressure that when you add up those partial pressures will add up to the total atmospheric pressure of 760. So nitrogen is makes up about 78.6% of the air that we breathe, and so the partial pressure at standard pressure is 597 millimeters of mercury. And that should be about 78.6% of 760, okay? Oxygen is the next highest one at about 21% or so. Water vapor has about 0.5%, so correspondingly low partial pressure. Carbon dioxide is less than 1%, 0.04%, and so the actual partial pressure is really, really low at 0.3 millimeters of mercury. The other law that we have to look at is Henry's law, and this determines the relationship between how soluble a gas is in a liquid and the pressure. Now, remember, think back to chemistry, and we didn't really talk about this at all last semester. Solubility is the ability to dissolve a substance into a solvent, right? The more soluble something is, the easier it is to dissolve it. If something is insoluble, they do not dissolve together. And so basically what this means, at a particular temperature. So if you keep temperature constant, the amount of gas you can dissolve in a liquid is proportional to the partial pressure of that gas. So if you look at the first diagram, if you increase the partial pressure, now if you increase the partial pressure, like in this particular case, they're increasing the overall pressure of the gas, which is going to increase the partial pressures of all the other gases. So how much gas you can dissolve of each gas you can dissolve in the liquid is going to increase if you increase the pressure, okay? Because that increase in pressure, so the example is the soda can right here, as you increase the pressure, that's going to force gas molecules into the liquid, and that's what the dissolving is all about. Now, when you release that pressure, so like here they took the lid off, decreasing that pressure. Okay, so when you take the lid off, you decrease that pressure. That's going to allow those gas particles to escape. And so your the solubility, how much you have dissolved in the liquid, how much gas is in solution is going to decrease until you reach equilibrium. So basically, the pressure of the gas dissolved in the liquid is going to be equal to the atmospheric pressure outside of the liquid. And so you're going to have gas molecules coming in and out at the exact same rate. And so the number of gas molecules overall remains constant. Okay, now, I would like to say, if anybody has a pressure cooker or an Instapot or something like that, that's one of the ways that pressure cookers work, is it increases the pressure inside the container. Also, when you're doing like bottling and stuff like that, you're increasing the pressure inside by forcing all that carbon dioxide in, then you cap it, so the carbon dioxide has to go into the liquid, and that's where the carbonation comes from. And so when you have a soda can and you open the can and you get that sort of that psh sound, that's all the gas in here escaping out. That's also why whatever you're drinking, like your soda or sparkling mineral water or something like that, fizzes, is because all that gas is leaving. Now, there's also a relationship that with temperature and all this, and colder liquids can hold more gas. So that's why if you open a soda, you put it in the fridge. The warmer the liquid, the less gas it can hold. The other thing that affects how much gas you can put into a liquid is the solubility of gases in various body fluids. And so we're primarily talking about dissolving these different gases in water. Carbon dioxide is highly soluble, so you can dissolve a lot at very low pressures. And so, which is good because it dissolves into your blood very readily, even though there's a very low partial pressure in the atmosphere. O2 is somewhat less soluble, so it's not as soluble as CO2, but still very soluble. Nitrogen gas is very limited solubility, but you end up with a lot of nitrogen in your blood because the partial pressure of nitrogen is so high. If we were to look at the plasma in the pulmonary vein, so this is the blood that is coming from the lungs back to the heart, the partial pressure of the CO2. So when you write partial pressure, so P is pressure, and then in subscript you write the compound that you're looking at. So the partial pressure of the carbon dioxide is about 40 millimeters of mercury. Oxygen is going to be a little bit higher because the partial pressure is higher at 100 millimeters of mercury, and then 573 millimeters of mercury for the nitrogen. Even though it is less soluble, the partial pressure in the atmosphere is significantly higher. As far as diffusion of gases across the blood-brain barrier, the direction that the gases go is the oxygen coming in and the carbon dioxide going out, or vice versa, is going to be determined by the partial pressures and the solubilities of the gas. It's also going to it's going to go based off the concentration, how much is dissolved in the blood versus mixed in the air, and vice versa. Gas exchange is a very efficient process. I think we mentioned that a couple of videos ago, sort of digging into a little bit. We kind of looked at some of the stuff. The total amount of distance that they have to travel is very, very small. The amount of tissue that it has to dissolve through is very, very small. The partial pressures across the blood-air barrier are substantial. The partial pressure of the carbon dioxide in your blood is higher than the partial pressure of the carbon dioxide in the atmosphere, and the oxygen is the opposite of that. Both gases are lipid soluble. That means they can pass across the plasma membrane very easily. The overall surface area is very large. Those alveolar sacs allow a lot of material to come in contact with each other, and that's where the actual gas exchange takes place. So the surface area is very, very large, and the blood flow and the airflow are both coordinated. So when you're returning blood, oxygenated blood, back to the heart, your lungs are full of carbon dioxide, so you're breathing out. Then when you breathe in, you're bringing that deoxygenated blood to the lungs to pick up the oxygen, so on and so forth. All right, so back to internal and external respiration. Remember, external respiration, that is bringing the outside air in and allowing it to come in contact with those tissues. So having the gas exchange taking place between the outside air and the internal tissues. There is a very low partial pressure of oxygen, so the blood arriving to the lungs has low oxygen partial pressure, high carbon dioxide partial pressure, and so that equates to a lot of carbon dioxide dissolved in the blood, not a lot of oxygen dissolved in the blood. So the concentration of oxygen outside is greater, the concentration of carbon dioxide inside is greater. And so this causes oxygen to enter the blood, carbon dioxide to leave the blood. The rapid exchange allows the blood and the alveolar air to reach equilibrium, so the same amount of oxygen on both sides, so on and so forth. Here's a diagram showing that particular process and looking at the numbers, if that helps. So the blood coming in, if you look, the partial pressure, we've got 40 and 45. If we look at the outside air, we've got a partial pressure of 100 and a partial pressure of 40. So oxygen is higher, carbon dioxide is lower. That's going to cause the O2 to come in and the CO2 to come out, giving us changes in our partial pressure that are equal to the partial pressure outside, right? And then this process just sort of keeps going in that rhythmic fashion. Internal respiration, oxygenated blood and deoxygenated blood are going to mix in the conducting pathways. The blood entering the systemic circuit is going to have lower partial pressure of oxygen as a result, down to about 95 millimeters of mercury. In the interstitial fluids, the partial pressures are going to be the same as what we saw in the venous partial pressures. And so that's going to set up a concentration gradient in the peripheral capillaries. So these are the capillaries in your tissues within the systemic circuit, are going to be the opposite of that of the lungs. And so that's going to cause the the gases to flow in the opposite direction. CO2 is going to diffuse from the tissues to the blood. O2 is going to go from the blood to the tissues. Here's a diagram that's showing that with those partial pressures right here, we've got that diffusion where we equalize with a partial pressure of 40 and of oxygen, partial CO2 pressure of 45, matching what the tissues are. And we can see that movement of oxygen away from the blood and the carbon dioxide moving towards the blood. All right, let's keep going because that one didn't take nearly as long as I think everybody thought. So let's talk about gas transport for a little bit. This is actually moving the gas around in the blood plasma. So the blood plasma by itself cannot transport enough gas on its own. That's why we have the red blood cells. The red blood cells are going to transfer the oxygen to the peripheral tissues, going to transfer the carbon dioxide away. It's also going to remove oxygen and carbon dioxide from the plasma, allowing other gases to dissolve into the blood, like nitrogen. Oxygen, we already talked about. Oxygen is going to bind to the iron ions in the hemoglobin, forming oxyhemoglobin. We've got about 280 million hemoglobins per red blood cell. Each hemoglobin can bind 4 oxygen molecules. That equates to, mathematically speaking, now the math is sound, and you can check with Miss Black about this, okay? That amounts to a metric boatload of oxygen that one red blood cell can carry. And we have millions of red blood cells, so it's several metric boatloads of oxygen that we can move. That gets into a phenomenon known as hemoglobin saturation. And so that's the percent of heme units that contain oxygen, that are bound oxygen. So oxygen is stuck to the heme groups, basically like a little magnet, at any given moment. Now there's a number of factors that affect this. This is an indication of how much oxygen is dissolved in your blood at any given time. Okay, the partial pressure of oxygen. The higher the partial pressure, the greater the saturation. Blood pH is going to affect it, also temperature, and the metabolic activity within the red blood cells. You can actually illustrate and predict how much oxygen is going to be in your blood under given circumstances by creating an oxygen hemoglobin saturation curve, or simply simply known as an oxygen saturation curve. And so that shows hemoglobin saturation in relation to partial pressure of oxygen. And that's going to give us the higher oxygen partial pressure. It's going to lead to greater saturation. Now it's a curve instead of a straight line, and I'll show you what that looks like here in just a second, because hemoglobin molecules change their shape every time an oxygen molecule binds to it. So there actually is a certain point where you continue to increase the partial pressure at the same rate. That doesn't really do anything for the oxygen saturation. And I'll show you what I'm talking about here in just a second. And so that helps at lower partial pressures. That allows you to bind oxygen more easily, but it also allows the next oxygen molecule to bind more easily. So here's an example of a saturation curve. And if you look at lower partial pressures, you have lower saturation. That kind of makes sense. Now it's a curve because at early levels right here, the rate at which we increase percent saturation based on changes in partial pressure increases significantly. And so basically what that means is small changes in partial pressure of oxygen lead to very large changes in the percent hemoglobin saturation. Now, as you notice, this curve starts to flatten out. So there's a certain point where changes to the partial pressure lead to smaller and smaller changes in percent saturation. Okay, and now it is important to note that it is impossible to have 100% oxygen saturation in blood, really in any liquid, because there's other molecules that are floating around in there that are taking up space. So like looking at this one, the best you can do is 97.5% saturation. So you're never really, in a natural setting, I suppose, going to get 100% hemoglobin saturation. Okay, so that curve that we just looked at is standardized for normal conditions. So a pH of about 7.4, temperature of about 37 degrees. These are normal sort of operating body temperature conditions, basically. When we have changes in either the pH or the temperature, if pH drops or temperature rises, then more oxygen is released, so the curve is going to shift to the right, and I'll show you that here in just a second. Now, if you increase pH, so your blood becomes more alkaline, or the temperature drops, it gets colder, less oxygen is released, and so the curve is going to shift to the left. And so here's what I mean by that. And shifting to the left, so the purple, this line right here, is normal pH, normal oxygen saturation. If you increase the temperature and decrease the pH, you get the blue curve. And so you're able to hold less, if you look, you're able to hold less oxygen. Basically, if you increase the pH and or decrease the temperature, you're able to hold more oxygen, so your percent saturation is higher. Okay. So this was pH. Temperature works the same way. So here's percent saturation at different temperatures. The normal body temperature is 38 degrees Celsius, so that's the orange line right there. At lower temperatures, if you notice, you have hemoglobin, you have oxygen saturation at 10 degrees Celsius at exceptionally high. Now, that's kind of a problem because the human body can't operate at 10 degrees Celsius, so there's that. I don't, off the top of my head, I'd have to go back and look up what that translates to as far as Fahrenheit is. And if you notice the red line, temperature is increasing, the percent saturation decreases. So you're able to put less oxygen in the blood at higher temperatures. Let's see. So in red blood cells generate ATP by glycolysis. So they do this. They form lactate and BPG, also known as 2,3-bisphosphoglycerate. This affects O2 binding and release. So the more BPG, the more oxygen that is released. As BPG levels rise, or if they rise based on an increase in pH or certain hormones. If BPG levels are too low, then hemoglobin won't release oxygen. Now, BPG decreases the affinity for oxygen, and it promotes the release of oxygen molecules. And so it enhances the ability for the red blood cells to deliver and release oxygen in the tissues that need it most. If you have muscles that are actively working and stuff like that, when you first start working out, if after a little bit your muscles start to burn, that's the buildup of this lactate and that BPG. That is going to cause the hemoglobin that comes through those muscles to release oxygen more readily, so the muscles can use that to start switching metabolic processes into aerobic respiration. And then that burning starts to go away about that point. But you have to be exercising for a while in order for that to happen. Okay, now fetal hemoglobin. Hemoglobin in a baby in utero is a little bit different. Structurally, it's different than adult hemoglobin. And so basically, it has a greater affinity for oxygen. It's going to hold on to more oxygen at lower partial pressures. And the reason why this is important is because the baby is in a liquid environment. Now, our respiratory system and our circulatory system is very good at extracting oxygen from the air. Now, we don't do so well in the water, and that's because there's more oxygen in the air around us than there is water. And so aquatic organisms have to work harder to extract as much oxygen as possible out of the water because there's less oxygen available. Same thing is basically that's happening with a fetus. A fetus is living in an aquatic environment during its time in utero. And so the fetal hemoglobin needs to be able to extract more oxygen, basically, and hold on to more oxygen from mama's blood by way of the placenta and deliver all that oxygen to the blood. So at much lower partial pressures, it becomes completely saturated than in adult hemoglobin. This gets into carbon monoxide. Carbon monoxide is commonly found in the burning of fossil fuels, in petroleum burning engines, so your car, the bus, motorcycle, truck, airplane, stuff like that. They release carbon monoxide. Anytime you burn something, you release carbon monoxide. Carbon monoxide binds very strongly to hemoglobin, and it's very difficult for the hemoglobin to release the carbon monoxide. And so that takes the place of oxygen in the hemoglobin. And so that results in carbon monoxide poisoning. One of the symptoms of carbon monoxide poisoning is bright red skin without a significant increase in temperature. But basically what you're doing is you're suffocating yourself because all that carbon monoxide, if you're exposed to large amounts to it, binds with your hemoglobin, and so the oxygen can't dissolve in there. In places like the United States, carbon monoxide poisoning isn't that big of a deal. In other places that have poorly ventilated homes and they use some sort of combustion to generate heat and for warmth and for cooking, carbon monoxide is a really big deal because your body doesn't register. It sort of bypasses what your body uses to determine if you have enough oxygen in your bloodstream. If you remember a couple of videos ago from the respiratory system, your body determines if you have enough oxygen or not based on the acidity of your blood, which is determined by how much carbon dioxide is dissolved in your blood. Now, the carbon monoxide technically isn't dissolved in your blood, so as far as your body is concerned, those receptors in your brain, you are getting enough oxygen. And so it doesn't do anything. It doesn't give you any warning signs like you're choking or something like that if you have carbon monoxide poisoning. So that's one of the reasons why carbon monoxide is dangerous. And pretty much all smoke detectors in homes nowadays, and they have been for decades, have a carbon monoxide sensor. They should anyway, I think. You may double check when you get home. It's a good idea for your home to have a carbon monoxide detector, especially by heating sources and stuff like that. Now, a lot of people, if you have an electric heater, that's not that big of a deal. But if you've got a fireplace or a wood stove, something like that, you really want to have adequate ventilation and a carbon monoxide detector just in case. That's Mr. Thompson's soapbox. I'm going to go ahead and climb down now and keep talking about blood flow and stuff like that. Carbon dioxide transport. Carbon dioxide is generated in aerobic respiration. I kind of talked about this a little bit. Maybe I'm talking about it here and we didn't talk about it in the blood videos or something like that. I don't know. So carbon dioxide is carried in the bloodstream in three ways. It's converted to carbonic acid and dissolved directly into the blood plasma. It's bound by hemoglobin in the red blood cells. Okay, and I mentioned the plasma one. So here's kind of what it looks like as far as percentages and stuff are concerned. Most of the oxygen is most of the oxygen makes it into the red blood cells, 93%. Some of it dissolves directly into the plasma as CO2. Most of the oxygen that makes it into the red blood cell is converted into carbonic acid, that's H2CO3. The other remaining 23% or so binds to the CO2, or binds to the hemoglobin, creating the carbaminohemoglobin complex, basically. From there, the carbonic acid dissociates into hydrogen ions and carbonate. The carbonate leaves the red blood cells back into the bloodstream. It works as a buffer. And the hydrogen ions are removed by the hemoglobin as buffers and neutralized, basically. That's it. So this is a diagram basically showing that gas exchange stuff that we talked about with those partial pressures and stuff like that. So here in the lungs, that alveolar space, that partial pressure is higher for oxygen than it is inside. So the oxygen is going to come in and it's going to bind with the hemoglobin, making that oxyhemoglobin. Some of the oxygen is going to actually dissolve in the interstitial fluid or in the blood plasma. From there, when we go to the systemic tissues, we're going to have a greater partial pressure of oxygen inside. That's going to push oxygen out, so that hemoglobin basically is going to release that oxygen into the peripheral tissues. At that point, that red blood cell is going to pick up carbon dioxide. Some of it's going to turn into the carbaminohemoglobin. Some of it's going to turn into carbonic acid and either leave the cell as carbonate or get absorbed by the hemoglobin and get buffered. Then it's going to make it to the lungs again. Here we are with the pulmonary capillary. Our CO2 is going to either be released by the hemoglobin or that bicarbonate that was pushed out of the red blood cell is going to get pushed back into the red blood cell, forming carbonic acid. The carbonic acid is going to break down into CO2 and water, and all of that CO2 is going to exit the red blood cell into the alveolar airspace, and then you're going to go, oh, like that. And what's really cool in that entire process happens like that, super duper fast. So it's very elegant and very fast, but it's very complicated, as I'm sure you're realizing at this point. Tell you what, this one went on for a decent amount of time. We're going to go ahead and call it. We've got one more that we're going to do after this. Mechanisms that control respiration and changes in respiration over time, starting from when you're a teeny tiny baby inside your mama's belly, not actually the belly, all the way to being you become a wizened old person, spewing your wisdom all over the young people, like Mr. Thompson. If you have any questions, send me an email, send me a reminder, ask me in class. Otherwise, I hope to see you again soon.